the derivative as rate of change, the instantaneous rate of change of f with respect to x at x naught is the derivative f prime of x naught equal to limit as h approaches 0 of f of x naught plus h minus f of x naught divided by h, provided the limit exists. In other words, we think of the derivative of a general function at x naught as being the instantaneous rate of change of our function. Now, what we have here, in this case, the function tells us position. So what we have is s equal to f of t. S is position, t is time. So this is position at time t. So here on this part, the position of a body moving along a coordinate line at time t, and shortly later at time t plus delta t. So here we have this point and this point here is based on time t and then later t plus delta t. And here in this case, the coordinate line is horizontal line. So this line is for s, and that is position based on what our time is. Velocity or instantaneous velocity is the derivative of position with respect to time. If a body's position at time t is s equal to f of t, then the body's velocity at time t is v of t equal to ds divided by dt equal to limit as delta t approaches 0 of f of t plus delta t minus f of t divided by delta t. So in this case, the instantaneous rate of change is often called the instantaneous velocity. So that's v of t as velocity at any time t. And that is derivative of position or derivative of s with respect to t or time. And what we have here, this limit is equal to limit as delta t approaches 0 of delta s divided by delta t. So here is what we have for velocity. Now here on this part we have graph for position at time t. So t is here on the horizontal line and s is our position vertical line. And based on what we have on this part, s is increasing from left to right. S is increasing. Based on that, our slope is positive. So this graph moving upward. Now, what we have on right side, here again, we have position at time t. So that is s equal to f of t. And here in this case, from left to right, our graph decreases. So s decreasing. Because of that, our slope is negative. So this graph moving downward. So this one was upward, but here on the right side we have downward. Now here we have speed, and that is absolute value of velocity. For speed, we cannot have negative numbers. For velocity, we may have negative or positive numbers. With speed, we don't have negative numbers. So we have to use absolute value of velocity. So that is absolute value of v of t equal to absolute value of derivative of s with respect to t. Having negative number for velocity indicate that the position is decreasing as a function of time. The one that we had here, this part was decreasing, and we are moving in the direction of negative numbers. And that's because this graph is moving downward. So remember that velocity includes the notion of direction as well as speed. So the derivative is very important when we try to analyze motion, because when we know the position as a function of time, the derivative gives us the velocity as a function of time. And when we analyze motion, we need to consider acceleration. So acceleration is the derivative of velocity with respect to time. If a body's position at time t is equal to f of t, then the body's acceleration at time t is a of t. So this a is for acceleration, and that is equal to derivative of v with respect to t. So what we have here is that is derivative of velocity with respect to time, and that is equal to the second derivative of s, or position, with respect to time. And here jerk is the derivative of acceleration with respect to time. So j of t is equal to dA divided by dt, or derivative of acceleration with respect to time, and that is equal to, and this is equal to the third derivative of position with respect to time. And this rate of change of acceleration is often called control. For example, what happens when you're driving your car in a straight line in a direction, and you control the acceleration of the car by changing your foot position on the accelerator pedal, or pushing harder or less hard on the brake. So what that means, you're trying to control the acceleration. Assume that you're in traffic and you suddenly try to stop your car. So in that case, you accelerate quickly. But when you need to stop slowly, you just push on the brake gently. So the rate of change of acceleration is how you control something by changing the acceleration. And it's often called jerk because in some application it's done by using quick changes or jerks. Now here let's use derivative to analyze the body's motion, particle motion. Here we have this example. At time t, the position of a body moving along this axis is, when we have here on the spot, is equal to negative t cubed plus 15 times t squared minus 72t meters. Part A, find the body's acceleration each time the velocity is 0. B, find the body's speed each time the acceleration is 0. Part C, find the total distance traveled by the body from t equal to 0 to t equal to 5. So here we need to know velocity, acceleration, speed. Finding velocity, that is the derivative of position with respect to time. So derivative of position with respect to time, that is equal to negative 3t squared plus 30t minus 72. And then here I factored to be able to find velocity when is 0. Because here in part A it's asking for the body's acceleration each time the velocity is 0. So negative 3 times t minus 4 times t minus 6. And this is 0 when we have t equal to 4 and t equal to 6. Now using these two, first we have to find acceleration and then substitute t equal to 4 and t equal to 6. So here we have acceleration that is equal to second derivative or first derivative of what we have here for velocity. So second derivative of our position with respect to time, or first derivative of velocity with respect to time. So here I have first derivative of velocity with respect to time. I'm using what we have here on that part. So that is equal to negative 6t plus 30. So this is what we have for acceleration. And now we have to use t equal to 4 and t equal to 6. So now finding acceleration when t is equal to 4, we can either use on this one, or here I factored negative 6. So it doesn't matter which one you use, you're going to have same answer. So when t is equal to 4, our acceleration is equal to 6 meter per second squared. And when t is equal to 6, our acceleration is negative 6 meter per second squared. Now for part B, we have to find when the acceleration is 0 by solving what we had here on this part, negative 6t plus 30. So here our time is 5 seconds. And now we have to use velocity to find speed. Speed is equal to absolute value of velocity. And from part A, velocity was negative 3 t squared plus 30t minus 72. Now using 5 instead for t. So substitute 5. Here we have negative 3 times 5 squared plus 30 times 5 minus 72. But we should find absolute value of what we have for velocity. So the answer that we have here is absolute value of negative 75 plus 150 minus 72. So add, subtract, all these here we have absolute value of 3, so that is positive 3, and this is meter per second. Now here, part C, find the total distance traveled by the body from t equal to 0 to t equal to 5. Here, what we had S was equal to negative t cubed plus 15t squared minus 72t. And if we try to find S of 5 minus S of 0 based on what was asking for t equal to 0 to t equal to 5, using this, we're not able to get the distance that we traveled. What we're going to have is net change of position. Notice that what we have here, this could be 0 if S of 5 equals S of 0. So there could be no net change in position. Or it could be negative or positive based on what we have for S of 5 and S of 0. So after finding the distance between these two, we may have 0, negative, or positive. So this is net change of position. But when we ask for distance traveled, we have to take to account of which way we went and how far in each direction. Now here on this part we have velocity, which is based on what we did in part A. That was equal to negative 3 times t minus 4 times t minus 6. So what's its value at t equals 0? So at t equals 0, we get negative 3 times negative 4 times negative 6. So that is negative number, and that is negative 72. So velocity is negative, and then as t increases, notice that this factor we have right here will be positive when t is greater than 4. So if t was greater than 4, this part, instead of having negative number, we will have positive. So starting from 0, t0, our velocity was negative, but when it gets to 4 and passes 4, this factor right here will turn to positive. What that means, we're going to have negative times positive times negative number. So we're going to have positive number for velocity. So what we're going to have for velocity is that our sign will change from negative to positive. So what this means, we moved in the negative direction from t equals 0 to t equals 4. And then from t equals to 4 to t equals to 5, we are moving in positive direction. So what we want is the net change from t equals 0 to t equals to 4. That would be s of 4 minus s of 0. So we want this distance. So this is inside absolute value, and then plus absolute value of s of 5 minus s of 4. In other words, we want to find the sum of these two distances traveled. So here what we have for s of 4 is negative 112, s of 0. So instead of t, I used 4, and the answer was negative 112 instead of t. Here for s of 0, t is 0, and the answer for s of 0 is 0. And now here on this part, s of 5 is negative 110, s of 4 is negative 112. Now this is equal to, we have absolute value of negative 112 plus absolute value of, here is negative 110, negative times negative, we have positive 112. Here is positive 2, and the answer is absolute value of negative number is positive number 112 plus 2, so the final answer is 114, and that is in meters. So this is distance traveled. Explorers on a small airless planet use a spring gun to launch ball bearing vertically upward from the surface at the launch velocity of 13 meters per second. Because the acceleration of gravity at the planet's surface was g sub s meter per second squared, the explorers expected the ball bearing to reach a height of s equal to 13t minus 1/2 g sub s t square meter t second later. So here is the expression for the position at time t, and g sub s is the acceleration of gravity on this planet. The ball bearing reached its maximum height 20 seconds after being launched, which was the value of g sub s. So what we have here, s is equal to 13t minus 1/2 g sub s t squared. The maximum height is at t equal to 20 seconds. So here in this case, whenever you throw a ball up in the air, at the instant it reaches maximum height, it appears to stop. So here we have position versus time, and based on what we have here, we're going to have a parabola, and because of having this negative sign for t squared, parabola opening downwards, and from what we have here, right here, we have the maximum height, and the tangent line is horizontal, and the slope of tangent line is telling us the velocity. So here we want to find the relationship between the time at maximum height and the position and the velocity. So finding velocity, that is equal to 13 minus 1/2 g sub s, and here we have t squared. So derivative as 2 times t, and now we can cancel 2 from numerator to denominator, so that will be 13 minus g sub s times t. So the point is, when we reach the maximum height, our velocity is 0. So velocity is 0 when we have maximum height, and that is when t is equal to 20 seconds. So here we have g sub s times what we have for t is 20. So what we have here is 13 minus g sub s times 20 is equal to 0. Now finding g sub s. So this is 13 equal to g sub s times 20, meaning that g sub s is equal to 13 divided by 20. So our answer for g sub s is equal to 0.65 meters per second square. So what we have here is the acceleration of the small airless planet due to gravity is 0.65 meters per second square. An object is dropped from a tower 163 feet above the ground. The object's height above ground t seconds into the fall is s equal to 163 minus 16 t squared. Part A, what is the object's velocity, speed, and acceleration at time t? Part B, about how long does it take the object to hit the ground? Part C, what is the object's velocity at the moment of impact? So here, based on what is given for s equal to 163 minus 16 t squared, finding velocity, that is derivative of our position with respect to time. So this is equal to negative 16 times 2 times t, and that is negative 32 times t feet per second. And now finding speed is absolute value of velocity, that is absolute value of negative 32 t, so that is positive 32 t feet per second. And acceleration is the derivative of velocity with respect to time. So here is negative 32 is based on this part, so negative 32 feet per second squared. Now part B, we want to find how long does it take the object to the ground with this means position, or s, that is 0. So here we have 0 equal to 163 minus 16 t squared. So solving for t, finding the answer here, t is equal to square root of 163 divided by 16. I round it to two decimal places. So here we have 3.19 seconds. So that is the final answer for part B. Now here part C, what is the object's velocity at the moment of impact? So we have to use this t 3.19 and find velocity. Our velocity was equal to negative 32 times t. So finding impact velocity, I can use this one that we have here, square root of 163 divided by 16, or the number that I rounded, 3.19. So I decided to have this square root of 163 divided by 16 and find the answer based on that without rounding t. So here I rounded the answer to two decimal places, and that is negative number, so it's negative 102.14 feet per second. Remember that speed was absolute value of velocity, and here having this negative number, that means it's going downward at the 102.14 feet per second when it hits the ground. Here on this part we have graph of velocity versus time. The accompanying figure shows the velocity equal to ds divided by dt equal to f of t meter per second of a body moving along coordinate line. Part A, when does the body reverse direction? Part B, when is it moving at a constant speed? Part C, graph the body speed for 0 less than equal to t less than equal to 10. Part D, graph the acceleration were defined. So now answering these questions, part A, when does the body reverse direction? It reverses a direction where velocity goes from positive to negative or goes from negative to positive. So here on this part, when a t is 0, where velocity is 0, now based on what we have here in this interval between 0 and 1, so here we have 1, our velocity is positive. Then between 1 and 4, here we have constant. And here on this part starts to decrease. And at this point when t is 5, again velocity is 0, moving downward, thus 1 decreasing. So here at this point we have reverse direction, and that is when our t is 5. Now here on this part, again moving up. At this point when t is 7, our velocity is 0, and now we have reverse direction from having negative velocity, again change to positive velocity. Now at this point again starts to move downward, but we stop here where t is 10 and velocity is 0. We don't have reverse direction at this point because it just stopped here. It's not moving downward. So what we have here between 0 and 1, in this interval we have positive velocity. In the interval that we have here on this part, 1 and 4, in that interval we have constant. And then here 4, 5, here again this part is positive, but at this point where t is 5 we have a reverse direction. Now in that part we have negative velocity, and again at this point we have reverse direction. Now here we have positive velocity. So our answer for part A, when does the body reverse direction? The answer is 5 and 7. So the body reverses direction at t equal to 5 and t equal to 7. So these 2 points. Part B, when is it moving at a constant speed? So here on this part, in this interval 1, 4, this part is constant. And remember that speed is absolute value of velocity. But what we have here, this is positive velocity, so absolute value of positive number, again is positive number. So our interval is 1 less than equal to t less than equal to 4. Now part C, graph the body speed for 0 less than equal to t less than equal to 10. So this one is speed, and that is absolute value of velocity. So the part that we have negative velocity was starting from this point up to this point. So this part is negative, but we should have positive for speed. So instead of this part, I should have this one here on top. So I draw this on top and then raising the support. So what I did, absolute value of negative is positive for speed. So this is our graph for speed. So what I had here, this graph in blue, that was for part C. Now I'm going to work on part D, graphing the acceleration where defined. So I'm going to raise this part and having what I had for our velocity. So now working on part D, remember acceleration is the derivative of velocity, and the acceleration will not be defined at these end points where t is 0 and t is 10. It's not defined at these vertices of the graph. So as we go from 0 to 1, so this point is 1, the velocity increase by 2 meters per second. So this point, so this part increases. So the slope of that line, which is the acceleration, is 2. So the graph of acceleration, we put the open circle right here at height 2 on the vertical axis, and then draw a little horizontal line and put open circle right here at height 2 over time t equals 1. And now from this point when t is equal to 1 to t equal to 4, remember that acceleration is derivative of velocity and derivative of a constant is 0. So because of that, we're going to use open circle here on this part for when t is equal to 1, and here when t is equal to 4, and draw this horizontal line. And here from this point when t is 4, velocity starts to decrease, and decreasing as by and here from this point when t is equal to 4, this one decreases by 2 units, meaning that our slope is negative. And here in this case, having negative 2, using open circle on this part. So from this point up to this point, so starting t equal to 4 to t equal to 6, we have negative slope. Connect these two, and now from when t is equal to 6 up to that point, t equal to 8, here this part increases. So now I have, for this point, t equal to 6, here we have this open circle right here on top. The other one is here, open circle, when t is equal to 8. Now connect these two. And now here, when t is equal to 8, starting from that point up to this point, t equal to 10, this part starts to decrease. And here in this case, our slope is 1. So this one decreasing, our slope is 1. Using open circle for where t is equal to 8. Here we have -1. And here we have open circle for when t is equal to 10. And remember that the acceleration is the slope of this line, and that is -1. So here we have -1 on this vertical line. Use that one to draw this line. Connect these two. So this is what we have. This one in orange color, that is what we have for part D graph of the acceleration.